Hello and welcome back to the course Students Guide to Information Theory and Coding. In today's session, we will learn some of the concepts related to the discrete memoryless channels. We have understood the information theory aspects in the previous session, and let us try to apply the concepts of the information theory to discrete memoryless channel. What we are going to cover in this session is we'll try to understand the probability model for discrete memoryless channel. We will take a quick review of the concept of entropy that we have understood in the information theory part, and we'll try to calculate the joint and the conditional entropies for discrete memoryless channel. We'll also understand the applications of this particular entropy calculations to a binary symmetric channel and to the variety of different types of channel. Okay, so good morning. Now we are in the last part of this particular unit where we are try to understand the concepts of information theory for discrete memoryless channel. And if you recall last one or two sessions where we try to focus more and more on this particular discrete memoryless channel and how we can apply the concepts of information theory for the calculation of various probabilities, for calculation of various entropies, everything that we have studied as far as the discrete memoryless channel. So a quick review we can take for last two sessions. We have tried to define the different types of probabilities for a discrete memoryless channel: the joint probability P of x comma y, the conditional probability P of x given y, and all these different types of probabilities that we define for discrete memoryless channel. A joint probability, the marginal probability of x, marginal probability of y, and the conditional probabilities x given y and y given x. After defining all these probability schemes for your discrete memoryless channel, we try to define the entropies for discrete memoryless channel. And in the entropy, we try to define the entropy h of x at the transmitter end, that is how much average amount of information transmitted by the transmitter, how much average amount of information received by the receiver. Then the conditional entropy is h of x given y, h of y given x, and the joint entropy h of x comma y. We have tried to derive the formulas for all these different types of entropies: h of x, h of y given x, h of x comma y, joint probability, joint entropy, and h of x given y. And we have also established the relationship between different entropies. And we also understand the physical significance of these different entropies as far as communication network is concerned. In last session, our focus was on solving some of the examples on joint and conditional entropy, and then the definition of the term called as mutual information. We defined the term mutual information, which is just a subtraction of final uncertainty minus initial uncertainty, and that particular formula we have established for the mutual information by creating the relationship between the mutual information and the various different types of entropies that we have learned. So the relationship, finally what we got for the mutual information is I of x semicolon y is h of x minus h of x given y, or it should be h of y minus h of y given x, or if I do the combination, I can get the third formula for the mutual information, that is I of x semicolon y is h of x plus h of y minus h of x comma y. That is the joint entropy, the individual entropy addition minus the joint entropy over there. Now, after defining all these particular entropies and mutual information, now it's time in this session to apply the concept of this mutual information to the real life applications. Now, what are the real life applications? We have to look into what are the different types of real life channels for a communication network, and we'll try to establish for these different types of channels how we can calculate this mutual information or the various different types of entropies. Now, while going for the real life application, our intention is to first understand the ideal case of a channel. And the ideal case of the channel is nothing but a discrete noise free channel, is called as the ideal channel. Why it is ideal channel? Because we understand you take any type of channel, whether it is a wired channel or a wireless channel, the noise is going to definitely corrupt your some of the data along with the channel. So there is no any channel in the world which is ideal or which does not have any particular noise interference. All our practical channels, some sort of noise interference we observed into that particular channel. So that's why, in order to understand the information theoretic approach, we will take first the ideal condition, and the ideal channel is nothing but a discrete noise free channel. Apart from that, we'll take another extreme condition where the channel is completely noisy, and the channel is called as discrete channel with independent input and independent output. Errors in the channel occur and the noise is present, but at the extreme end where we do not expect any particular information transmission. These two extreme cases first we will try to understand, and then we will apply to the real time channel, the real time channel, how we can calculate the information theoretic aspects. So let us begin with the first channel, that is called as noise free channel. Now noise free channel, I will understand the concept of the noise free channel by simply looking at a matrix, a joint probability matrix of that particular channel. Now, the joint probability matrix is P of x comma y. We understand on the x-axis there are random variable capital X, on the y-axis random variable capital Y. So this element is P of x1 comma y1, x1 comma y2, x1 comma y3, like that. This is how we have earlier defined the joint probability matrix. Now, if I want to look at to this particular case of noise free channel, what is ideally I can look at is, this is my first symbol, second symbol, third symbol, like that. I have n number of symbols that I am going to transmit from the transmitter towards a receiver, and at the receiver also I am going to receive certain number of symbols at this particular point. Now a channel is a noise free channel, and as it is noise free channel, it is not going to corrupt any of your data. Suppose here I'm transmitting x1, then there is a guarantee that I will receive y1 only. There is no possibility that the x1 is transmitted and y2 is received. If I am transmitting x2, there is a guarantee that only y2 will be received. If I am transmitting x3, there is a guarantee that only y3 will be received. And if I am transmitting xn, there is a guarantee that only y1 will be received. As channel do not have errors, channel is free from noise, we have only one combination, x1 transmitted, y1 received, x2 transmitted, y2 received. That's why if I look at the joint probability matrix over here, I am getting only components in the diagonal part of the matrix, that is p of x1 comma y1, p of x2 comma y2, p of xn minus 1 comma yn minus 1, p of xn comma yn, and all rest of the elements, they are going to be by default 0, because channel does not contain any noise. It's complete example of noise free channel. So, being joint probability is simply a diagonal matrix, we have very clear clarity. There is no any randomness available. The things are going to be certain because x1 is transmitted, y1 is received. There is no any other probability of happening. That's why this particular channel is referred as the ideal channel for the transmission purpose. Now, if I look at for joint probability, I have diagonal elements. Similarly, if I calculate its conditional probability, now we can understand that in conditional probability, we don't have any condition on dependency. X does not depend upon y, any other value of the y. That's why both this p of x given by y and p of y given by x, they are going to be the matrix with diagonal element as unity, the diagonal element as unity. So this particular values will try to give me the values of dependent entropies exactly equal to 0, because there is no dependency of y on other values of x or of x on other values of y. Therefore, the conditional entropies for noise-free channel, they must be exactly equal to 0. So that's the reason why the p of x given y is going to become an a matrix with all diagonal elements unity, and which will give me this conditional entropy 0. Now if the conditional entropies are 0, if I look the formula for joint entropy is generally h of x plus conditional entropy is 0. So the joint entropy for noise free channel is going to be equal to h of x, or it is equal to h of y, or that could be equal to minus summation I is equal to 1 to n p of xi comma yi log of log of p of xi comma yi. So it's a joint probability multiplied by the logarithm of joint probability, but in this case x and y, they are exactly equal. That's why their notation is exactly same. Here also there is a I, and here also there is a I. Both the case there are I, and that's why single summation sign from I is equal to 1 to I is equal to n. Otherwise, in normal formula, we observed here two summation signs, one for I for x and another for j for y. But in this case, both x and y are exactly same. We have only single summation formula. I is equal to 1 to n p of xi comma yi log of p of xi comma yi. And if I look at the formula for the mutual information, it is also h of x plus h of y minus h of xy, but here everything is exactly same. That's why the mutual information is also exactly equal to h of x or h of y or h of x comma y, which means that the information transmitted through this channel does not depend on what was sent or what was received. It is always completely predetermined by the transmitted content. So in the ideal case of channel called as a noise-free channel, we have the entropy, joint entropy exactly equal to h of x, exactly equal to h of y, and therefore the mutual information is also equal to h of x, h of y, and h of x comma y. This is one ideal case of say noise channel. What ideal case of the channel. Few more observations what we could have for noise free channel, that each transmitted symbol is in a one-to-one correspondence with one and only one received symbol. That is what we have understood from our earlier discussion. The entropy at the receiving end is also exactly same as that of sending end, and the individual conditional entropies are equal to 0. So that is what for noise free channel. That is the case of ideal channel that we discussed over here. Now, let us take its extreme condition. What is extreme condition? The condition in which a lot of error is present, and what that information that I'm transmitting, I'm not going to receive at the receiver end. Almost every information is going to be corrupted, and that type of channel is called as discrete channel with independent input, independent output. Now let us try to understand what is meant by independent input and independent output, right? So in this channel, there is no correlation between input and output symbol. Now independent input, independent output. Input is also independent, output is also independent. We don't have any correlationship between x and y. Earlier we have correlationship y dependent upon x dependent upon y, x comma y, right? So here there is no dependency between x and y. X is independent, y is independent. If I look at the joint probability matrix for such type of independent input, independent output channel, then we can observe that p of x comma y has same probability in the first row. That is, the probability of all symbols in the first row is p1. Probability of all symbols in the second row is p2. Like that, the probability of all symbols in the mth row is going to be pm. in our earlier case, we observe it is P of 1, 1 comma 1, 1 comma 2, 1 comma 3, 1 comma m, 2 comma 1, like that. But in this case, we observe that we have same probability, equal probability for all the symbols in row number 1, equal probability for all the symbols in row number 2, and the probability of row number 1 is not dependent upon probability of row number 2. They are completely independent event. So if I do the summation of all this probability pi from I is equal to 1 to m, I observe that it should be 1 upon n, because n number of rows that we considered over here for this particular matrix. N identical, sorry, where n is the n identical columns that we considered in this particular matrix. So that is going to be equal to P of Yj, and therefore P of Xi will be n into Pi for this type of independent input, independent output channel. Since the input and output symbol probabilities are statistically independent, we can observe that P of the joint probability P of Xi comma Yj will be P of Xi multiplied by P of Yj. This is from the concepts of the probability. We understood that whenever the event X and Y are statistically independent, the joint probability will be the multiplication of Xi multiplied by P of Yj. And we observe that P of Xi will be n into Pi, P of Yj will be 1 by n. So the product of the joint probability P of Xi comma Yj will be n into Pi into 1 upon n, that is going to be equal to Pi, where I is changing from 1 to m. Similarly, the conditional probability, P of Xi given Yj will be P1 of Xi, that is n into Pi, and P of Yj given Xi will be P1 of Yj, that is 1 upon n. So this is how we can calculate the joint and the conditional probabilities of statistically independent events. Yes, any doubt?
सर तुमचा आवाज ब्रेक झाला.
Now I'm audible?
Yes, sir.
Okay.
For this slide, very
Okay. So for this slide, once again, I'll repeat the content that I'm talking about independent input, independent output channel, where in independent input, independent output channel, there is no dependency between input and output. Therefore, X and Y are statistically independent event. They have same probabilities on every row and such n number of columns. So the total sum of the probability will be 1 by n. And we can define the joint and conditional probabilities for this independent input, independent output channel as P of Xi comma Yj will be n into Pi upon 1 upon n, that is Pi. P of Xi given Yj will be P1 of Xi, that is n into Pi, and Yj given Xi will be P1 of Yj. Now why this is P1 of Xi? Because there is no dependency between Xi and Yj. So Yj doesn't play any role, and the conditional probability is not exist, whereas it will be related to Xi only. Similarly here, Yj does not depend on Xi, so P of Yj given Xi will be P1 of Yj. That's it. So how we define the joint and conditional probabilities? Now let us calculate their joint and conditional entropies. H of x comma y will be minus n summation I is equal to 1 to m pi log of pi. Why? Because it's a joint probability. P of xi comma yi is pi. Joint probability is pi, and our formula says it is pi log of pi from I is equal to 1 to m multiplied by n, because there are n number of columns that we have to take into consideration. So that is going to be my joint entropy. You can note down these formulas, because one example will solve on this independent input, independent output channel, where by using this formula you have to calculate the joint and conditional entropies for independent input, independent output discrete channel. Similarly, h of x If I try to calculate, it will be n into pi log of n into pi, and if I take n common, minus n summation pi log of pi from I is equal to 1 to m minus log of n. And for h of y, it will be minus n into 1 by n log of 1 by n, that is going to be equal to log of n. And if I calculate the conditional probabilities, h of x given y is exactly equal to h of x, h of y given x is exactly equal to h of y, because it satisfies the probability conditions. So the last two equations shows that this channel conveys no information. Look at the extreme end that I'm taking into consideration. In first case, noise free channel, whatever you are transmitting, exactly same thing that you are going to get it. But in independent input, independent output channel, you are conveying no information, because h of x given y is exactly equal to h of x, and h of y given x is exactly equal to h of y. There is no dependency between x and y. You are transmitted something and you are getting something different. There is no correlation between what you are transmitting and what you are receiving. That's why this is the channel which conveys no information in the system. For this particular channel, if I calculate the mutual information, you can understand that the mutual information for this channel is definitely going to be zero, because it does not carry any information. And if I look at the formula for the mutual information, it is h of x minus h of x given y. But x given y is also h of x. So h of x minus h of x, that is going to be 0. And therefore, this channel does not convey any information. The mutual information for this channel is going to be 0. So, noise-free channel versus channel with independent input and independent output are two extreme cases. In one case, it's an ideal case. Noise-free channel is an lossless channel. Ideal case, it will transmit the signal as it is, but the second one, it does not carry any information. Independent input, independent output is completely lossy channel, because information is not been communicated. So these are two extreme, and all your real world communication channels are in between these two extreme cases. They are neither noise free, they are not independent input, independent output. They have capacity to transmit certain amount of information from one end to another end. They might be lossy channels, but not completely lossy. They never be lossless channel. Some amount of information is been lost, which you may able to recover at the receiver by using some different techniques. But this sort of practical channels, we can able to calculate the entropies, we can able to calculate their mutual information also. So I hope I try to explain you the two extreme conditions for the communication network channel, a noise free channel, and an independent input, independent output channel, and their entropies and their mutual information calculation. Now, our focus further will be on real communication channel